and hazards to aviators. These are the things they want to look out for. And then I give them a little taste of what it's like to be a soaring pilot and working on wave. So the sources, there's a lot of great information out there. This advisory circular by the FAA is 23 years old. They have it posted online as a black and white PDF, but it's very full of valid current information that really hasn't changed. It's not very technical in nature, but it's very informative. All kinds of organizations, Soaring, Society of America, glider clubs, etc., have great websites. And then, of course, for the more technical knowledge that a meteorologist might look at, these are some of the other sites available, and there's a whole lot more. I was really pleased to see that Walter showed 4 or 5 sites that he uses. It would take a while for an average pilot to learn how to use those products. I tend to steer pilots towards aviationweather.gov for one-stop shopping to give them enough awareness to make good decisions. So some of this might be, of course, a review for the professional meteorologist, but necessary conditions for wave to form. Obviously, we need some winds aloft that are pretty strong, generally 20 knots or stronger at mountaintop level, and in a direction, in the same general direction, without a layer above that that's a completely different direction that would create wind shear and shape up the top of the wave. Topography, we're blessed in North America to have lots of mountain ranges aligned north-south. Anytime we have our prevailing westerly winds and strong winds at the lower altitudes, we have the potential to have mountain wave form. If you have a peak like Mount Shasta, Mount Rainier, Mount Hood, that sticks up way higher than all the surrounding peaks, you could get mountain wave form off of that with a wind from any direction, just off of that lone peak. Stability, generally, stable atmosphere is preferable for wave to form, something resistant to convection. And I ask folks, so if you had the Sierra Nevada or the Teton Range or something where in the summertime we have a lot of convective activity, if the atmosphere was super stable, you wouldn't really, if it was unstable, I should say, you would see towering cumulus, development of thunderstorms over the mountains like we typically get in summer afternoons. But for wave to form, you need stable atmosphere, higher pressure is great, and I start to explore more. So for a student or someone who doesn't know much about aviation or weather at all, if they were to say, what is this thing you're talking about, mountain wave? This is just kind of my generic explanation about how, stable air mass blows up and over the top, it's compressed, pushes down over the top of the mountain and rushes down the lee side. And because of the stable lapse rate, it wants to return to the altitude it started from. So it's not going to continue going up and building a towering cumulus. It wants to rush back down the lee side. And when it compresses at the bottom and it springs and it bounces back off, the stable air mass below on the lee side, that's what forms the up and down oscillations. So in a classroom, when I teach this, I usually take a tennis ball and toss it across the floor and watch it bounce and show them how each successive bounce gets a little bit lower in the height that the ball bounces, and then it eventually tapers out and begins to roll. So it's a visual example of a similar kind of physics. So the obvious typical visual indicator that pilots learn about are the standing lenticular clouds, the altocumulus, and in a lot of cases, if there's enough moisture higher up, the cirrocumulus lenticularis clouds. So I showed this as from the backyard looking south down the Bitterroot Valley. The mountains are out of the west, out to the west of the picture on the right-hand side, and you can see how the wave comes up and the lenticular forms. This would be the trough in between, and then the next wave crest over here. And you can tell that the wind is blowing from right to left in this picture because of the curl of these little rotor clouds curling up and over. So I show that to pilots and say the rotor is really the big hazard that pilots you want to look out for when flying in the vicinity of mountain wave. So the diagram shows that rotor, again, usually forming underneath the lenticular. In mountain flying, and a lot of literature in aviation safety talks about the lee side rotors. This is all in a very micro scale compared to what we're talking about here. But the lee side rotors on the backside, anytime you have a wind more than 20 knots blowing up and over the top of a mountain, don't fly on the lee side at low altitude, like at 500 AGL, especially in a low powered aircraft. So this is where a lot of accidents have occurred in the mountains because people flew in this area. Now, over here, the beauty of this one is a lot of times this rotor, okay, you may have temporary loss of control, but you got flat terrain underneath and you got a lot of room. You're not really above the terrain. So these rotors can be very severe. So that's the message to the pilots. Hey, the other thing that back in Weather 1 branch, two pilots learned that in order for clouds to form, you have to have moisture rise to the point or the altitude at which the dew point and the temperature spread meet and the moisture condenses. Okay. But in mountain wave, people go, well, if the wind is blowing 30, 40, 50 knots aloft, how come that cloud stands still? And then explain how the air rises, it cools to the dew point temperature, and you see the visible cloud, but then the wind continues to flow down, temperature dew point spread opens up, no longer a cloud. So basically the wind flows through the cloud and back out the other side, and then up here you form another cloud. So if you don't have enough moisture in the atmosphere, you can get dry wave. We can get very smooth, strong lift and wave lift in low humidity times of year, say in the desert, and still have wave but have no visible clouds. So just because you don't have a lenticular doesn't mean you can't get mountain wave to go flying or soaring in. I tell them about the structure. We talk about wavelength being the distance from one wave crest to the next, and amplitude. So amplitude would be if you sheared this right across horizontally in the middle, the distance between where from the midpoint down to the trough, or from the midpoint up to the crest, that would be our amplitude height.
I'm so sorry to interrupt you, Kurt. Do you mind if we click on the hide on the bottom of your screen where it says join.me is sharing your screen?
Oh yeah, okay. I didn't know that was showing on yours. Oh,
yeah, if you just hit hide, it'll hide that, and then it's just been blocking some of your words. Thank you so much.
All right. Okay, you bet. Appreciate it. Okay, then how do we know how long the wavelength to be? Stronger winds tend to produce longer wavelengths, and if it's really strong aloft, there would be less amplitude, and we'll talk more about that when we talk about travel wave. The slope and the height of the mountain's lee side, so you get a range like the Tetons or the Sierra Nevada. Tetons are 13,700 feet is the highest peak, and the Jackson Hole sits at 6,300 feet. So there's a very abrupt, steep lee side that when we get the right conditions, that the wind can pour down the gravity wind a great distance, 7,000 vertical feet. So it has a lot of force, a lot of volume of air bouncing off the lee side valley floor. And same with the Sierras. The towns of Bishop and Lone Pine, they're down at about 4,000 feet, and the top of Mount Whitney is 14,000, with lots of other peaks around there at the 12 and 13,000 foot level. So very abrupt and very steep lee slope tends to really amplify mountain wave. You can get mountain wave, of course, in other mountain ranges in the U.S., like in the Appalachians, but if they're lower, more rounded mountains, you're probably not going to get huge amplitude waves over there. And then a general rule of thumb, yeah, they could be as little as 2 miles or 25 up to 25 miles apart, but 8 to 10 is typical, most between one wave crest and then next. Amplitude, again, we just talked about the steep slope on the lee side is what really promotes major amplitude, and stability on the lee side that resists convection. So if you had very unstable atmosphere on the east side of the mountains, and you had lots of big thermals and covering cumulus, and you're not going to have those conditions conducive for mountain wave. Now, the interesting thing about cat and mouse game that glider pilots have to play is when you're on tow and you're trying to work your way up to catch the wave, which might be, several thousand feet above the valley floor, you can either stay on tow behind the tow plane and go to a higher altitude and then release when you're in the wave. And that gets really expensive when you stay on tow. And it ties up the tow plane for a long time for the next person who wants to get a tow. Or if there are thermals, weak thermals, moderate, some kind of solar heating there on the lee side, and you can work and scratch your way up, release, try and work some thermals, and sometimes you can make it up into the waves. So the other thing I state at the bottom here is how the amplitude can be re-energized by terrain downwind. So the next slide is of the northern Rockies north of Missoula, Montana. This is the Swan Valley. If you had strong wave conditions and you had wind coming up and over the Swan Valley and down and maybe a couple of waves and troughs, and then bam, it hits this next one and gets re-energized, and the next one and the next one. And then by the time you get out here over the little towns of Choteau and Augusta and out towards Great Falls, you can get some massive wave having been re-energized. For a pilot, I would say, think about a turbocharged engine, how the exhaust gas gets channeled back through for combustion. It really gives the engine an extra boost when you have a turbocharger. Similar kind of analogy with the wave lift being re-energized. And for this reason, there have recently been some pretty significant cross-country flights and gliders where they work the wave off of one mountain range, turn downwind, and punch through the sinking air and catch the wave over here at the next mountain range and go back up. And then you can go great distances now going downwind from mountain range to mountain range when there are several parallel ranges off this. Okay, amplitude. Generally, for soaring, if you're about 3,000 to 6,000 feet above mountaintop level on the downwind side, that's where you're going to get start getting your good lift for wave soaring. You get lift up to 1,000 feet per minute. And then wherever there's large amplitude tends to have more severe rotors below, as opposed to trap lead wave, which we'll talk about in a minute. Here's a computer model of radiosonde-based lift and sink in the area. This is looking north, this diagram, from the south end of the Owens Valley looking north. This would be the Sierra Nevada. This is the Owens Valley. The White Mountains in Nevada, right here is about where the Nevada state line. And then you have these other ranges over by Austin and Tonopah into Nevada. So again, you get, you would think ridge soaring would be really good, but in this condition, on the upwind side, yeah, you get some bumps up and down. Then you get the severe downslope gravity wind, and boom, this is where your first good soaring is going to be. And so if the mountaintop level here is, say, 13,000 feet, between 13, 16, 17,000, in this range is where you're going to get some great soaring. And up here you get another area where there's high altitude, clear air turbulence could be a hazard for aircraft up at the 25 to 40,000 foot level. And again, this shows the rebound of the troughs, the lift, the crests, and the troughs. Where it's blue, it's sinking air. Where it's brown and reddish colors, and yellow, it's lift. And you can see how it's compressed. So these are measures in meters per second of lift. So if you had 5 meters per second, you're going to get 750, 800 feet per minute of climb out of a glider. The different types of mountain wave, this probably is familiar to a lot of you. The 3 types we're going to talk about separately. Vertically propagating wave is interesting. This is where you get some of that clear air turbulence at the higher altitude. And again, you might not get a whole series of oscillations like you may get with trapped lee wave, but the initial bounce off the ground produces significant wave at higher altitudes. And it's interesting how they tend to tilt back upwind a little bit. And wave is basically the propagating wave that tilts back even farther, and you get this hydraulic jump zone right here where it really curls back. This can create some really severe turbulence for low altitude operations, not only in this rotor, but anywhere in this area too. You might get wave with really strong updraft and downdraft. So literally the wave can break and result in that clear air turbulence. And if the wave isn't breaking up at high altitude, sure, you might get some strong lift and sink areas of up and down air, but you're not going to get something so severe that it causes structural damage up high, unless you're going really fast. You get something like the wall really hard. And then down here, your main turbulence would be, of course, the rotor at the low altitudes, where generally pilots will generally be flying down there. So here's a couple of images that really kind of illustrate. Oh, remember how the atmosphere and air has fluid properties, and what a perfect analogy. The hydraulic jump, and it springs back and curls over, just like these poor raptors getting thrown out of the boat. So doesn't look like a lot of fun, probably isn't in an airplane either. Okay, lee wave. Energy doesn't propagate nearly as strong vertically like with high amplitude everywhere like we just saw, but usually the biggest factor in the formation of trapped lee wave is the layers of air above the wind is quite a bit higher. So if we had, say, wind at the 12,000 foot level that was 30, maybe at 15 or 18,000 feet, it's 35, and it's not that great of a difference. You're probably going to get vertically propagating wave. But if your winds at 12,000 feet might be 35, but at 18,000 feet it's blowing 60, I mean, that stronger wind is just going to shear off the top of any amplitude that wants to develop, and that'll limit the wave height and allow it to rebound and become trapped lee wave further downstream. When I demonstrate this with the tennis ball in a classroom, I might set up a table and I'll bounce the ball really hard on the floor, but it bounces up to the underside of the table, so it can't go very high, and show how that table kind of limits the height that the tennis ball can bounce. And it's a good visual demonstration of that. So when it's trapped to the lower altitudes, it's said you can find your trap. A lot of times the rotors down here, you might get small rotors, but I don't think they're nearly as severe as the ones where you have major amplitude vertically propagating or breaking wave above. And sometimes trapped lee wave can extend. For example, the wave coming over the Colorado Rockies in the fall and early winter, and you can get 40, 50 knot winds coming over the Rockies, and mountain wave forming up, and pilots have reported turbulence as far to the east as eastern Kansas, all the way to Missouri. You can get the effects of the wave way far downwind, hundreds of miles. So here's an image of what trapped lee wave might look like to a glider pilot, just little ripples and lots of them. So here's a satellite image of the state of West Virginia and Virginia. And here you can see multiple trapped lee waves in succession, extending all the way across the state. So how do we predict or forecast wave? So class, for the next hour, we're going to break this equation down by each element and describe how to derive the eddy dissipation rate. And the class usually goes, "What? No, don't do that to us." So there's got to be an easier way for the average pilot to figure this out. So instead of us being required to know how to go through these equations, voila, we have one-stop shopping with the graphical turbulence guidance on the forecast on aviationweather.gov. What a beautiful thing. They even give you a color scale of eddy dissipation rate. All the math is done for you. given in colors, and you can see, hey, on this particular day when I was in the Bitterroot Valley right here looking at mountain wave up in the sky, I could see where the strong mountain wave was on this scale. So, and you can click, for pilots that haven't used this before, you can click on different periods of time, look what it's going to do 6 hours, 10 hours, 12 hours down the road, and at different altitudes. And if you click on this, you can look at all different altitudes and times. So it's a very, very useful one-stop shopping. If you only had time, 3 minutes to look at one web page to say, is this a good day to soar? This might be one to look at. So I like to look at winds and temperatures aloft. This is an example of, for example, on this day that I was observing wave, GPI is Glacier Park International Airport up in Kalispell on the west side of Glacier Park. Here at 9,000 feet, winds were 290 at 37. At 12,000 feet, 290 at 47. And then at 18, 290 at 42. So the wind speed, yeah, it increased by 10 knots, went down a little bit, but it didn't really change a whole lot in terms of wind speed, and the direction stayed the same. So any wave that was produced downwind of that is not going to be sheared off in amplitude and causing trapped lee wave. It's probably going to be some pretty good vertically propagating waves just on the east side of Glacier Park or in that area of the state, which would be over here. I also look at the jet stream maps, and we're going to take a look at them in a couple of slides. So the other phenomenon I noticed here is, okay, we have massive high pressures in 2 or 3 places just west of the Northern Rockies, and I can only imagine that each of these rotating clockwise and pushing winds out, this one is going to pick up and amplify and turbocharge, as I say, some of the wind coming off this high and really give it an extra boost as it gets sent up and over the Northern Rockies near the Idaho-Montana line and over into the Great Plains. So that's another good cue that, what I'm seeing, this is one of the things causing it. Of course, I look at air mets for turbulence and look at the altitude and what they're calling for. Obviously, turbulence could be caused by a number of things. Could be convective activity, could be just cold front passage, could create generating air met for turbulence. I also look at the jet stream. On this particular day, when I was looking at the mountain wave over the Bitterroot, the jet stream was not a factor contributing to that, but at certain times when the jet stream is lower and it's right over us, yeah, you can get mountain wave formed by lower altitude jet stream. SIGMET, I like to look at them, and this one's a great example of some high SIGMET, probably breaking wave. Look at 24 to 33,000 feet, occasional severe turbulence due to mountain wave activity right there in the SIGMET. That was great to see that, and that was over the Sierras. And then some low-level wind shear was going on also that same day. PIREP, we talked about PIREPs times today. There was one submitted by a 737 that was crossing over the Sierras westbound. They reported this about the time they got to Modesto, and they had encountered moderate, occasional severe turbulence up to 25,000 feet. That was a day when they had some pretty good lenticulars on the Owens Valley, and the soaring pilots were enjoying flights at 20,000 and higher. Okay, I show pilots this the SKU-T chart. Walt was talking about this earlier, and obviously since then there have been a lot of graphical models that have been developed that they don't render the SKU-T obsolete, but they sure augment it. And I think it's one of the most underutilized charts by general aviation pilots. A lot of pilots don't learn how to use them. Soaring pilots do. But I think if more general aviation pilots learned how to use and read a SKU-T chart, they would learn a lot about where there's icing, what kind of convective activity there's going to be, where the basin and the tops of the clouds are going to be, etc. So in addition to just the wind barb showing the direction and wind speed at the different altitudes. That alone is a graphical depiction of the winds and temperature aloft that I showed a couple slides ago. Beautiful picture of soaring up in the wave over the Owens Valley on the leading edge of the first wave on the lee side. Hazardous aircraft, the main one being the rotors again, and at higher altitudes, the breaking waves. So this aircraft on the right is fresh wreckage from many years ago up in Alaska due to rotor from wave. That was actually a B-29 Super Fortress bomber, like the one that dropped on Hiroshima. That aircraft, pretty large, powerful aircraft, a bomber that could not outclimb the rotor and the photographs and the results of the mountain wave. Okay, the rotor clouds, you know, if I were a glider pilot out in the summertime and I saw wispy little clouds like this, I would just think, oh, there's thermals, not enough moisture to really create a puffy cumulus cloud that is going to start powering that and work for lift under it. Certainly doesn't have a flat base. Just looks really innocent, like if I flew over there, not a big deal, but in the context of mountain wave, this rotor is curling up and around, and it may be akin to flying your airplane through a wash machine. If you got too close or tried to fly through that, you're going to get possibly tumbled with momentary loss of control and, you know, worst case scenario, structural damage and potentially in-flight breakup of the airframe. So speaking of, this is right out of that advisory circular. Right in the very beginning, they talk about accident statistics. There's a whole list of aircraft that have encountered mountain wave, lee side rotors, and on a lot of the comments it says lee waves present, wind rotor suspected, strong lee wave, mountain wave here on this one. So one in particular of interest in March of '93 in Anchorage, this is right out of the NTSB report. Boeing 747, shortly after takeoff, they were climbing out between 4,000 and 8,000 feet and experiencing fluctuations in airspeed of plus and minus 35 from the speed they were trying to target. Uncommanded rolls, 45 to 50 degrees of bank that were uncommanded, and other aircraft in the area reported downdrafts of 4,000 feet per minute, and then strong updrafts where they couldn't maintain altitude and were going up like crazy. This one sheared off an engine. They were able to get it back to the airport and land it, believe it or not, and there were no injuries, and it was a miracle they were able to get that back. This is taken from one of Sarah's presentations. Thank you very much for that. I was pretty interested and fascinated by the fact there is no ICAO criteria, you know, defined for severity. And so these are some numbers they came up with within the Weather Service aviation folks to define what really is constituting moderate or severe turbulence. So this gives us a little bit of a measuring stick that is good for pilots to know, especially if you're going to submit a pilot and you can tell them what kind of speed and altitude changes you experienced in the course of your encounter with turbulence. This is a classic example back in '64 of a B-52 that was flying at about 14,000 feet going north near Colorado Springs on the east side of the Rockies during mountain wave, and it sheared the tail off. And again, these folks were able to fly this aircraft around, maintain control with some difficulty, but they were able to maintain control and get it back on the ground and land it. So it's a real testament to their crew resource management and their skill as aviators to use all other available resources to control that aircraft. But it made it back, which is amazing. So for light aircraft flying near a mountain wave, I recommend in any case, you know, if the winds are more than 20 knots, passing over a mountain range, even if there's not wave on that day, avoid flying lower than 1,000 feet above the mountains if it's blowing stronger than 20. That's just a good rule of thumb. And If you're going to cross over the peaks, try to be at least 1/2 the height of the peak as measured from its base to the top. So if the base and the valley floor is 7,000 feet and the summit's like 11,000, there's a 4,000 foot vertical difference between the base of the peak and the summit. So take half of that and try to stay at least 2,000 feet above the top. So that's a good rule of thumb. And then another one, how to fly the airplane if you do encounter strong areas of sink. Definitely pitch down, fly through it towards lower terrain, get out of there, and don't attempt to outfly it with power and pitching up like you would normally try and maintain a given airspeed that we call VY when you're climbing out on takeoff, for example. It's better to sacrifice altitude, turn around, really cover some horizontal distance and get out of that area of sink as fast as possible, even if you have to lose a little bit more altitude. The longer you spend time in that sink at a slower airspeed, the more altitude you're going to lose, and it's going to take you a lot longer to get out. So again, try not to fly in clouds. If there's a lenticular or rotor cloud, avoid it. Maintain your VFR unless you're in a flight plane, and keep your speed below what we call maneuvering speed, which is to prevent any structural damage to the aircraft. If you maintain airspeed below maneuvering speed, your aircraft will probably be okay. All right, for soaring pilots, the wave is the playground, just like Walt was talking about earlier. We like to seek that opportunity any time we can. So obviously the best conditions for wave, now you can get really great wave flights if the wind's aloft or 60 or 80, but now you're talking about more major league conditions. And if you're just a recreational soaring pilot or you're just learning how to soar, vertically propagating waves are going to give you a pretty major league ride. It's going to have really strong lift, but if you're going for a personal best or an altitude gain, and you really want to learn how to go to, and you're equipped and ready and prepared for a high altitude flight, that's the kind of wave you want to look for. The lower, more benign trapped lee side waves, like some of the ones we saw in the photos earlier, a little more user-friendly for beginner pilots. The rotors underneath them are probably less severe than, say, this one that we see underneath the lenticular in this photo. Then I explained to folks how the wave tends to shift. If I were walking on the beach here and once in a great while a wave may come in and all the way come up to where I'm running and get my feet wet. But, you know, then 5 minutes later, the onshore flow might be over here or over here. So if I put a time-lapse photo on this wave cloud over the Bitterroot Valley and video it, it would show it ebb and flow and move just like waves in the water pulsing and coming in and going out. So I learned that as a sailplane pilot because one time I took a tow and the tow plane pilot said, "Hey, I just towed the last guy over to this spot and he was able to catch the wave right there. I'm going to take you to that same spot." He took me over there and I stayed on tow and we looked and looked and looked and there was no more lift anywhere. But 3 or 4 miles away to the north, boom, there was some wave lift in a completely different place in about 20 or 30 minutes after the first person. So for sailplane pilots, sometimes you have to stay on tow a lot longer in order to find lift, or you release from tow and you have to sometimes work hard in lighter thermals to make it up to the base of the wave before you can start climbing. You can actually get in sink that's so strong you can't get away from it and land out. I've had to do that, land on dirt roads in the middle of nowhere. More than anything else, that just creates a logistical problem because you have to have a retrieve set up and your logistics with somebody to come and pick you up and take the wings off the glider and put them in the trailer and tow you home. So this is another serious one. If the winds aloft are really strong, you could be maybe 3 or 4 miles downwind of an airport that you plan to land at, and the wind is so strong and you pitch down and you don't make it back to the airport because you're in such a strong headwind. So always have a way out, somewhere to land. Rule number one in flying gliders is look around in all directions below you in kind of a cone, and always say, if I got drilled, or I had to sink out, or I sank out and I had to land somewhere, where would I go? Where am I going to land? Always have that in the back of your mind. And same with power pilots. We always teach them to anticipate worst case scenario. What if my engine quits right now? Where am I going to land? Always ask yourself that question. Again, for beginner cross-country pilots and wave pilots, so cross-country flights we normally think of for gliders is much easier on a thermal day in the summer. You're going up on one thermal, flying across to the next thermal, and hopscotching from one to the next, going cross-country that way. Cross-country flight in wave would be a little bit more difficult for someone learning because of the strength of the sinking air in between the areas of lift. So that would present a real challenge for a glider pilot if they weren't ready to land out. And then there's lots of other unusual hazards associated with soaring gliders in high winds. So obviously in our federal aviation regs, anytime you're above 14,000 feet, you have to have oxygen on, but oxygen systems can malfunction. Sometimes the canopy, it's so cold, just from exhaling air, it starts icing up inside the canopy if it's really cold. You have to dress for it. If you're not prepared, you don't have gloves and a warm coat. Traffic in that airspace at high altitude, you're going to see aircraft going by at 300-400 knots whizzing past you. So got to be heads up and looking around. Flight in extreme sink, yeah, you always have to be prepared. If I get in some sink and I can't get back to the wave and get back into the lift, I may have to land out in potentially in a remote area where you don't necessarily have cell coverage. Always have a plan and a way out, somewhere to go to get down safely if you need to in an emergency. More hazards. Sometimes the winds aloft are so strong and you're just ahead of the leading edge of the lenticular cloud, and you got to be really careful that you don't slow your glider down by pitching up and then backing into instrument conditions, into the wave. Gliders usually don't have gyroscopic engine-driven vacuum pumps like airplanes do, and you don't have the instruments needed to maintain your awareness of what's up, down, right, and left when you're in a cloud. So if you fly into instrument conditions, into a cloud, it's real easy to lose control, and there have been fatalities in soaring as a result of that loss of control and breaking up of the glider because the number exceed speed has been exceeded. Spatial disorientation, loss of control, and exceeding the maximum speed that the structure of the aircraft is able to withstand could happen. So we're all familiar with the term, a picture's worth 1,000 words. When I see this, that's what I'm thinking. Okay, what would I be thinking if I were the person flying this glider? Okay, I'm above the rotor that's down here. You can see it right here. But the strongest wave, the lenticulars are above me. I might be in wave lift. This person's variometer is showing they are climbing in some weak lift, but where's the strong wave? How can I get up? But do I want to go up much higher? Because if I get up here, it's a pretty solid overcast. There's not a lot of VFR conditions up here. So looking down, I'm thinking, okay, where do I need to go to avoid being in the sink? So obviously this side of the cloud is where the lift is. This is the sinky side. Stay in the leading edge. But what if this layer starts closing up below me? I don't want to get stuck in between layers. So visually maintain awareness of where the ground is and always have a way out. If you need to get down, you got to maintain visual, not IFR, and get down underneath the clouds if you have to. And sometimes you're soaring, you go, oh, that wave over there looks so inviting, but I'm not high enough to get there. And then you're looking for a thermal, trying to go up. This person in the right is flying right near Hood River, Oregon. That's the Columbia River in the background looking across onto the Washington side, and that's Mount Adams in the background over here. Beautiful wave, potentially off Mount Adams or that part of the Cascades. But this glider pilot has a lot of work to do before they can even think about shooting across the river and getting over to the wave. May or may not be able to make it there today. Okay, flight at high altitudes often involves going up, or let me rephrase that. Strong waves sometimes gives you an opportunity to climb to higher than 18,000 into the Class A airspace. That's totally illegal, and unless you are operating under an agreement that the FAA has with glider operations in several parts of the country, they're called wave windows. You would need to call the Air Route Traffic Control Center at some point in advance, usually an hour or two before you are intending to fly above 18,000. And that wave window can be opened and activated. You have to follow a lot of local protocols and comply with the provisions of the waiver that we're allowed to do that. So it's a real serious thing. It's a privilege that the FAA has granted us in certain locations. And so we have to respect that and only fly above 18,000 if you have that authority or authorization to do so on that particular day. So again, we were talking earlier this morning, Walt was talking about the Perland project. So you may have already know the answer to this third one, but these are just some records, 35,000 feet right here in Montana, U.S. record, 49,000 feet. That may now be broken. I don't know if that's still the current record over the Owens Valley. And the world record is the Perland project, as Walt was talking about before. And that's the one where he was telling us they went to 76,000 feet in 2018. They tried again last year, didn't quite get that high. And the goal, it's a multi-year project. They'll be back down there in the fall and ultimately trying to reach 90,000 feet. So there is a link if you go to their webpage, perlandproject.org, that Walt was showing us. There's some great video clips and stuff on there. It's a pressurized glider specially made for this river attempt, and pretty ambitious project, very professionally managed, and a great operation. So my final recommendation to GA pilots is, hey, if you can step away from your powered airplane and get your glider rating and start soaring, it will blow you away. It will open up all kinds of doors in your awareness to really working with meteorological conditions to sustain your flight. It teaches you so much about weather, so much about airmanship, decision making, so much about precision flying. Highly, highly recommend all pilots spend some time soaring in gliders. So that's the conclusion of this. Do we have any questions?
Sorry, I was just getting my audio back there. Thank you so much. Great presentation. It is always nice to hear more about this. We do soaring forecasts out of the Reno office, and there's a large soaring community down in Minden, and also I know Truckee and other areas, all in the lee of the Sierra. So it was great hearing all that information from you. Right now, I am not seeing any questions showing up, but I will give it just a minute. If anyone has any questions, please feel free to type it into chat. Well, Kurt, looks like you did such a good job. No one has any questions. If anyone thinks of anything after the fact, we have Kurt's contact information up there on that slide, and we'll also be passing out the information afterwards. Looks like we are just a little bit ahead of schedule today. It's amazing. Yesterday we kept trying to catch up, and today we have been ahead most of the day. So what we will do is we will take a break here. We already have a break scheduled. Why don't we go ahead and come back in approximately about 15 minutes or so. So it would put us at 1:45 Pacific, 20:45 Zulu, or 2:45 Mountain. We'll see you then. And Kurt, thank you again.
Okay, you're welcome. Happy to be here.